everyone. I'm Mert from Texas Tech University. I'm a PhD student there. And today I would like to talk about examining the benefits of a secure and distributed architecture. Sorry. I'm sorry. Yeah, I need. So this. Thank you. So this project is made possible thanks to the collaboration between a lot of universities. And the motivation for this work for xBGAS comes from the fact that the traditional PGAS systems, or where you have distributed systems, rely on a lot of software overheads to communicate between different nodes to do the get operations such as get input. And there have been some software paradigms, PGAS paradigms, that have been in use to support such systems, such distributed memory systems. What xBGAS originally aimed to do was to extend the base global address space on RISC-V by using 128-bit pointers, where the lower 64 is just the regular addressing, and the higher 64 is responsible for encoding the remoteness. This project is based on RISC-V. And one thing that you might be mistaken is this is not a direct replacement for the RV128. Unlike a 128-bit addressing system would work, we separate the remote and the local so that no compatibility issue occurs with a regular 64-bit addressing system, at least on the local level. So some of the use cases of xBGAS, I'll go through this fast. HBA flat, mmap.io, cloud BSP, and HPC PGAS. So the architecture looks something like this, where you see two nodes in this figure. The memory interface and the namespace look-aside buffer resolves whether part of the memory resides on a remote node or a local node, and then makes accesses accordingly. And typical pointer consists of a base address and an extended address field. So this project, as is, already addresses some of the concerns, like the scalability, generalizability, and the software overhead that would be associated with a multi-node distributed memory system. But how about security? For the security aspects, you might see a problem that might result in such an extended architecture, where you see that the attack surface increases, especially for traditional attacks. And you might see how the memory safety has become a bigger and bigger issue by the headlines that you might encounter. For instance, multiple different research accounts to about 70% of the safety issues on a traditional computing system to be associated with memory safety. And for instance, in some of these projects, you see that on Mozilla's report, I believe, about 50% was just use after free vulnerabilities. And you can see that that strengthens the motivation for a secure distributed architecture. And you might see there are already talks about how do we secure all these C and C++ language bases for memory safety issues. And there are some projects that already cover these. Here, in this case, we talk about the architecture-based ones. And you will also see some folks here talking about, I believe, even CHERI and Xeno projects. They also are complementary to these. Goals. And let's talk about a little bit of how we can secure these by the use of capability systems. So capability systems offers a design pattern for us to secure the scope and spread of damage of memory safety issues. There have been multiple capability-based addressing systems throughout history. And for this talk, I would like to leverage the work that have been done at the University of Cambridge on CHERI, along with its complementary ARM system, the Morello platform, for how we can show you a use case of a secure extended system. So University of Cambridge, just CHERI project, basically offers an architectural protection model with capability tags, with a capability area. And this is to mitigate vulnerabilities in C and C++ trusted computing bases. And they also have a prototype platform model called ARM Morello. And it is based on a Neoverse. And it is completely a CHERI-enabled architecture. And what we do is, how can we demonstrate an xBGAS prototype system on the ARM Morello boards of CHERI that adapts the CHERI protections, and showcase the first that xBGAS's regular benchmarks and applications can be used. Second, that we can showcase the evaluations of performance along with some security evaluations. Can we mitigate any use after free issues? Can we mitigate any out of bounds reads, and so on? So this aspect of the project consists of a few steps. First, for hardware platform, you'll see that we use ARM Morello, and we simulate the existence of an xBGAS platform on such a system. Since this does not, the ARM Morello platform does not offer xBGAS extensions on hardware, you'll see this work relies on the simulation of such a system. And this also, since also xBGAS is currently implemented on RISC-V, we had to do some ARM assembly translations, some API changes, and adaptations for the applications we run. So let's look at an overview of these two platforms to see what we need to address here. You can see that a pointer on xBGAS consists of 128 bits. Again, the upper is extended address, lower is the local address. On CHERI, similarly, the local address is still the local address, but there are also some bits that are spared for encoding information such as bounds, permissions, object type, and a tag for the validity of such an address. The object type is currently an unused field on CHERI on the part of University of Cambridge. And what we propose in this simulation is to use the object type field to encode the remoteness information, since it offers us enough of unique IDs to use case for a prototype for a simulation system. And a few of the challenges for a simulation is, how do we handle the inter-process communication? And how can we transfer these tags, these capabilities, over different nodes? For the scope of this project, we gloss over a few things, but we have a proposal of an idea where what we do is we separate the higher bits and the lower bits into two and send them, and so we basically push the problem to the network side. How you communicate between nodes and send these as two different packages and reassemble them. This relies on the assumption that there is a privileged operating system that can reassemble bits. CHERI offers some methods for that, and that's where the solution exists. For simulating this, what we have done is we experimented on QEMU FVP, then right now an actual ARM Morello board. We translated some of the xBGAS RISC-V instructions to something that would be equivalent for a simulation purpose. And since the CHERI architecture itself and the Morello board itself doesn't have the architectural extension that we have, we model the behavior of PEs by just using threads. So simulation is limited in scope on that. And what we do is we propose minimal changes to how an xBGAS app operates as is, so that we can run the benchmarks and test vulnerabilities accordingly. So here are the runtime tests and benchmarks, what we've been working on. What we want to showcase, what we showcased is the transfers such as gets and puts can be demonstrated on the low-level runtime. Some shared global configurations can exist, and some collectives can be demonstrated. So for this, we took a group of applications, such as the GUPS, the gather operation, matrix multiplication, reduction, and broadcast. And we demonstrated them on the Morello platform under a thread scenario to emulate or to simulate how multiple PEs would behave. This is the board that we use, the specifications of the board that we use on the Morello side. And here's an example output of how GUPS can perform about 35 million updates, 33 million updates over the course of 20 seconds in this thread-based scenario. And since this is a simulation, you might see that it's a long time. For some of our experiments, you can see how we have adapted, and you see a demo of how a matrix multiplication runs. And for us to call the benchmarks to be a successful port, we need to be able to showcase that similar to at least how OpenSHMEM works, it should be able to scale between different number of PEs and still have the same ratios, although it would be a factor of X slower than how a hardware would implement since it's simulation. It should still not introduce extra overheads. And to demonstrate that, we did some basic performance evaluations on GUPS, and where we can still see, although it is an X factor slower than an OpenSHMEM implementation, since we are emulating different PEs, not on hardware, whereas xBGAS would have proposed, but on threads, we still see the scalability that is similar to what we expect. And on different applications, such as GUPS, gather, or matrix multiplication, you can see that the characteristic of an application is not that different from what we expect. So that is like the base case of how we can evaluate whether such simulation is good. There are also some broadcast to 8 runs that we made. We can measure that. Those also run quite well. I don't know if it's too small here. Similarly, we demonstrated such simulation on the reduction operations. And that moves us to the security part. Since the benchmarks and the performance evaluations seem reasonable for such a system, how can we evaluate what we propose here? Because we want a secure distributed memory architecture, right? And what are some adversarial evaluation suites that we have available? First, from University of Cambridge, and then from Arizona State University, there are some memory security vulnerability test suites. And you can see that we tested the simulation based on these suites. You can see some of them were quite unsuitable to simulate via threads. That's why we skipped those here. And I'll show you a few cases of how a run of these tests perform on the Morello platform. For instance, you see an out-of-bounds read here. On the right, you see the original version. On the left, you see the adapted version. And we can see that we cannot do an out-of-bounds read on such a system because of an in-address space security exception, which is the case that we expected. Here, then we talk about use after free, where a program continues to use a pointer after it has been freed. And since the freed memory can be allocated again, it can be filled with different data. Using the old pointer, it can lead to some unpredictable behavior. And in this case, in this demo, this is still an ongoing effort, so we're still continuing to investigate the issue. We still didn't mitigate use after free vulnerability at this point. So again, since time is a little short, I try to go fast and cut some things last minute. But the conclusion is we are exploring the benefits of a secure and distributed architecture by simulating an adaptation of the xBGAS on a capability system. And you can reach out to me to brainstorm, to talk more, or ask questions about this project. You can read more about the project or look at our adapted runtime through these QR codes or links. And if you want to learn more about the xBGAS on RISC-V, a lot of repositories are already available on the project, but you can also reach out to me. So thank you for your attention, and let me know if you all have any questions.
Questions? We have one over here. So I have a couple of questions. One is that if you have a global pointer that's remote, does the capability checking involve multiple transactions across the boundary, or is it, or does the whole cluster have the same model of capabilities?
So in the way that we currently dismiss the capability transfer model, the idea, there are two approaches that we discussed, and I did talk to this about to the Cambridge folks too. One of them is either there exists an OS that is the almighty OS that checks whether a capability is still valid, or we figure out, and for this we need some API from CHERI perspective to figure out if we can just reconstruct a capability. That's what I meant by pushing the problem to the network, where you unbundle the two fields and then rebuild them on the other side. So I push these problems to the OS side and network side a bit, but those are still open questions.
Okay.
Two directions exist, though.
So the second question I had is, do you have access to many Morellos? I mean, it's a limited production thing, as I understand.
It is out of my control. It took a while and a lot of effort and a lot of contacts, but we have had access to a Morello board.
So, but Cambridge also has their CHERI system running on FPGAs, both in-house as well as on Amazon AWS Cloud, where you can scale it to multiple FPGAs. Have you thought about using any of those?
No, because the goal from the start point of this project was to also demonstrate, because since xBGAS originally exists on RISC-V, we didn't have a hardware platform to demonstrate how xBGAS would function.
Yeah,
so we wanted to...
I'm saying Cambridge has RISC-V implementations on FPGAs on AWS Cloud.
Oh, okay, then I wasn't aware of
Yeah.
that. Sorry, then I don't know. I would look into that.
Yep.
Sorry, very similar question to the last, but I'm particularly interested in the CHERI tags and how you get those across between nodes, because the really important thing in an architecture is that you can't control them in software. So as soon as you're having to raise them up to a network stack and transmit them, suddenly man in the middle and all sorts of security problems arise from that. So have there been any particular thought of the tags?
For the tags, the validity tags, I don't have a short or good answer for that. That's still worthy of more investigation. The only answer that I have is I push it to software, and yes, I raise more attack vectors. So we're looking into it is the only thing I can say at this point.
All right, let's thank Mert once again. Cheers, Mert. The xBGAS goodness continues. xBGAS. No, Olaf.
Hi everyone, my name is CHERI from Texas Tech University.